Hey, awesome Physics 30 students. Mr. Jukley here, looking at Unit 3, Lesson 7 on page 124. If you don't already have your workbook there, you can go ahead and get that one out. This is not much of a mathy lesson. Lots of explanations in this one, so you don't necessarily need a calculator. But this is a pretty cool lesson, actually. I really enjoy this one. So it's all about applications of this electromagnetism, and we've spent the last few days talking about a bunch of different things, but the solenoid being one of them. And we mentioned with the solenoid just how important that is for our lives today. Pretty much anything electrical that we have deals with these solenoids in some way, shape, or form. So today we're going to look at a couple things. Couple applications that use these, and you'll see for like very different things. So the first thing to check out, I'm actually going to get you to watch this video. I won't put it up here, but if you go search it, like, so the person, his name's Destin, from Smarter Every Day, he gets the views. He made the thing, so that's only right. But you could either type in the actual link itself, or you could check out just in your YouTube, type Smarter Everyday Tattooing. And this is pretty cool. You'll see the solenoids and you'll see some of the ideas, and it's got a fantastic visual. So if you want to go ahead and put your video on pause here, go for it and check out this video, and then come back and yeah, we'll see a couple other pieces. So there you go. Put it on pause now. I'll talk to you in a minute. Cool. So we're back. Another piece that we want to look at is speakers. Another very cool website to check out is this Animagraphs loudspeaker. You could probably just Google search that rather than having to type the whole thing in, but Animagraphs loudspeakers goes through in more detail than we actually need to know how speakers work. But we will look at them a little bit here. So essentially with speakers, you've got several different parts. So you've got a coil. Perfect, and the coil has current running through it in different ways, and it's going to create a magnetic field. Then we've got a permanent magnet that's going to interfere with that magnetic field from the coil. As they're interfering, the coil is going to be pushed back and forth, and it's attached to this this cone over here. The cone is going to be pushed back and forth, and that's what's going to create our compressions and our rarefactions in the air, if you remember what those are from Physics 20. There are sound waves. So as the cone pushes this way, it will create a compression, and as it pulls the other way, it'll create a rarefaction, and that creates, again, the sound waves that travel through the air, and the sound that we would actually hear. Now it does it very quickly, and does it in multiple different I guess frequencies at the same time almost, which gives us our sound, our bold sound that we hear from speakers or from my voice. Not that I have a bold sound here, but the sound that we hear coming out of speakers. So let's check this out in a little bit more detail here. So here is the idea of our speaker. So I've got my permanent magnet here. It says it's just a north. It would also have a south, obviously, but we've got my permanent magnet here. And then I've got some current running through the solenoid, the coil of wires that are wrapped around the speaker. And then here is, so let's see, no, that's going to be coloring. There we go. So here's our cone that we can now see. And that cone's going to be pushed back and forth, creating those sound waves. So which way is the cone going to move in this particular situation? So first thing to think about is what hand rule we want to deal with. I would want to use left hand rule number 2. So get out your left hand rule number 2. Remember, it's what's shown in the pictures in the bottom right over there. So curled fingers, pointing thumb. Our curled fingers represent the direction of the current around the solenoid, and our thumb represents, in this case, we're just going to keep it as our north pole. Remember, it's also the direction of the magnetic field through the center of the solenoid, but our thumb for this case is our north. Cool. So lots of people kind of get confused, like electrons moving this way across the solenoid. That's true. They are kind of moving from one side to the other across the solenoid, but that's not actually what's important for us. What's important is how they're moving around the actual wires. So it looks like they're going up the back They're coming out the front, and all of the electrons are going to be coming down the front of that solenoid and up the back of that solenoid. That is more important than if they're moving left or right or whatever. It's the actual path of the electrons through the wires. So let's see, got to push that button there. I get my left-hand rule out. I know that it's coming, the current is coming down across the front. So I'm pretending, and I'm using the one that I've got now above the solenoid here. I'm pretending that my hand is wrapped around that solenoid, or let's get a color that we can actually see would be helpful. So the solenoid goes through the middle, there's the coil of wires, and my hand is wrapped around, and my fingers are tracing the lines or the wires that the current is running through. So the only way, if I've got that's going sort of how we've got it drawn here, the only way that my thumb can really point is to the left, which means I'm going to be creating a north pole on the left side of that solenoid. So I'm just going to clean this up a little bit here and move a few things out of the way. Awesome. So if that's my north pole on the left-hand side of the solenoid, do norths really like being next to norths? Not so much. So we're going to have a magnetic force, Fm, on the entire speaker, the cone, I shouldn't say the entire speaker, but the entire solenoid, the cone that it's attached to, and it's going to, the whole thing is going to push out this way. So to answer the question, the cone is going to move towards the right, and it's going to create a compression in the air as it pushes and squeezes that air. So hopefully we get that. I'm going to clean this up a little bit here, and I'll show you kind of the next little piece. So let me erase everything. And of course, you can rewind and check things out if you want to. I'm just going to change one thing, one little tiny thing. It's going to be this side is now negative, and this side over here is now positive. So the current, when we trace that current around, is now going up the front in every situation and down the back. So you notice I have two pictures of my hands here. I'm going to get out the other picture of my hand. I'm going to rotate it so that my fingers are going up the back. It's as if I'm holding that whole thing in my hand. And notice how my fingers, this is actually kind of neat. I didn't know it would be behind the writing, but notice how my fingers are pointing in the same direction. So now my thumb is pointing towards the right, so this is going to be my north pole, and if that's my north, well, my south has to be on their side. And you might say, okay, well, now I've got a north right next to a south. There's going to be a magnetic force pulling the whole thing towards the left, and therefore the cone's going to move towards the left, and it's going to create a rarefaction, an area of lower pressure. And it's going to do this. So the speaker does this, goes back and forth, so positive, negative, negative, positive, back and forth. I kind of screwed that up a little bit there, but does it very, very quickly, and that's what creates the sound. So again, if you check out this Animagraph website, you'll be able to see a very cool animation of that. But I hope that kind of makes sense for people. So there's one of them, a speaker. The next one that we want to look at is a lifting electromagnet. So you see the actual electromagnet up here, and it's lifting some sort of huge piece of steel. This always reminds me of the movie The Brave Little Toaster. Brave Little Toaster. The boy goes off to college. It's been a long time since I've seen this, but I believe the boy goes off to college and all of his stuff wants to come with him, and the toaster decides to go on a cross-country mission to follow his boy to his new dormitory. And there's a scene where they're in the junkyard and the brave little toaster gets picked up by the lifting electromagnet and then is going to get crushed. Oh, it's dramatic. You should watch. If you haven't seen the Brave Little Toaster, you should see it. But let's check out how that lifting electromagnet works. So I've got some hands in the way. Let's just get those over to the other side. So a lifting electromagnet is actually fairly straightforward. Essentially what we've got is we've got a soft, oops, that's not a felt pen at all, soft ferromagnetic cores. And those soft ferromagnetic cores, I'm going to erase this in a second, but they are essentially through the center of a couple solenoids. And you see a couple solenoids there. Do you remember why it would be soft ferromagnetic cores? If you got this gigantic lifting electromagnet, if it's hard, it's going to be more of a permanent magnet, and it's going to pick up that gigantic piece of steel or whatever it is, and it's not going to be able to put it down. A soft ferromagnetic material, remember, you can switch the domains really, really quickly. So you can pick up that piece of metal, you can move it to another place, so move it over here, and then you can put it down when you turn off the current running through that. So typically you would also have a switch here, but I guess we don't really necessarily need to show that. Cool. So if we want to look at why these create such strong magnets, we got to go through and we got to think about, okay, it's still left hand rule number 3. My curled fingers are still my current running through the wires around the solenoid, and my thumb is still now the direction of the magnetic field and the north pole. So direction of the magnetic field through the center of the solenoid and the north pole of the electromagnet. So again, it's really important that I trace the direction electrons are going. So electrons are flowing with the gray there. It looks like, and the solenoids is what I'm really interested in, they go around the back and then across the front in this direction. So every single one going across the front in this direction. And then again, it goes around the back. And then look at over here. Look at over here. I'm going to highlight that in red. Now they're going across the front in this direction. Perfect. Perfect, perfect, perfect. So we get out hand rule number 2. Can we predict the poles of the electromagnet? So I'm just going to use blue. I'm going to say, okay, we're looking for that. And we're looking for that. So considering as electromagnet. So try out hand rule number 2. Put the video on pause if you want to. But get out hand rule number 2 and see if you can figure out those 2 question marks. Is it north or is it south on each of those? Cool. So let's check it out. Let's have a look here. So I need my current going around the back. Let's see. And across the front in this direction. Perfect. So notice how my fingertips are lining up with those arrowheads. This is a new discovery for me. I didn't think it would work out that well. So my fingertips, if I'm pretending that I'm wrapping my hand around this thing, my fingertips across the front are all pointed towards the left. So I think this is appropriate for this side. I may just get rid of this piece to get it out of the way. So this is what my hand rule would look like for the left-hand side. So my thumb is pointing upwards. That means that the north pole must be up on this one. And if the north pole is up, the south pole must be down. So it's not so bad. Let's get out the other hand for this one. Well, it's still hand rule number 2. It's just the other picture of my hand, I should say. So in this case, now my fingers are curled across the front like this. It's like my hand is wrapped across the front. It's still hand rule number 2, left hand rule number 2. And notice how my fingers line up across the front with the direction that's pointing. And which way is my thumb pointing? Pointing downwards, so I'll leave this one on this side, and the thumb points towards the north, so that means it must be, that's not a felt pen, must be a north at the bottom here and a south at the bottom, or sorry, at the top on that side. Cool, so we predicted the poles. Now essentially what this makes for us, once we've got that, is a horseshoe magnet, and horseshoe magnets are very, very, very strong magnets. And we can look at sort of why they're strong magnets if we go back to thinking about this domain theory. So we've got a south on the left and a north on the right. So if I've got this metal object and it's not in any magnetic field at all, we remember that those domains are totally 100% scattered. The domains, remember, are little tiny magnets, so chunks of the material that all organize themselves into little tiny magnets, chunks of atoms that organize themselves, and the arrowhead is a north. And the arrow tail is the south of that little magnet. So once this gets closer, oops, sorry, I'm skipping around here. Once this gets closer, the lifting electromagnet gets closer, it's actually going to arrange those domains and see if you can figure out, you can put it on pause here, see if you can figure out how it's going to arrange them so that it would be attracted. So things that we know is that norths attract south, and vice versa. So essentially, we're going to have all of the domains aligning here and here. So we're going to have a magnetic force attracting in those 2 spots, and a magnetic force attracting, I shouldn't say in those 2 spots, but attracting my metal object to the north pole, and a magnetic force attracting my metal object to the south pole. So they're going to align themselves so that it is now attracted. Cool. Very, very good. There's a lifting electromagnet magnet. Holy, I'm having a hard time talking today. Lifting electromagnet. Next one to check out is an electric bell. These electric bells still used as fire alarms and things like that in our schools. So let's check out how an electric bell works. So essentially, we have similar sort of ideas where I've got electrons that are flowing from my power source. In this case, I've got a switch. The switch could be like our fire alarm kind of thing. So when someone pulls the fire alarm, they are closing that switch. When the switch is closed, it's actually pretty nice. It just lets electrons flow through. Right? So if it's open, electrons can't pass. If it's closed, the electrons can flow through. So once that switch becomes closed, let's just clean this up a little bit here, electrons flow straight through. Back to my original color. Perfect. And we can trace them all the way around. So I'll just trace electrons flowing this way, flowing down. They go through this weird little device that we'll talk about in a second. So it's a contact screw and an armature that is on a spring. All right, so through the contact screw, through the armature, through the spring, and then into the solenoids. Perfect. Now, if I wanted to look at these solenoids and think about, okay, well, which side is which? Like, am I going to have a north pole? I'm going to have a south pole? Again, we get out our hand rules. We say, oh, well, the current is going down across the front. Every single wire's here. And then it goes, let's see, down, down the back, and in the bottom solenoid, it looks like it's going to be going up across the front. So if I get out my hand rules, let's just have a look here. I think this one, it's still hand rule number 2, by the way. So left hand rule number 2. No, I don't think that's for that one. It must be this one. Perfect. So I get my hand lined up. Yeah, perfect. So I'm wrapping my hand around that solenoid. And then my fingers are coming down across the front. So looking at my thumb, the only direction that my thumb can point, so I'll leave that one there for that one, is towards the left. So that means the left must be my North Pole. Perfect. So I already kind of used up that picture where I look like I'm tanned. I'll look at the one where I look like I'm very pale, and we'll look at the other one. So in this case, on the bottom solenoid, the electrons are going up across the front. So I have my fingers so it lines up as if they're going up across the front. The only way that my thumb can point is towards the right. So that means that right must be my North Pole. And if right is my North Pole, well, then left must be my South Pole. Perfect. So we've got that figured out. We're making that electromagnet very, very similar to the lifting electromagnet, except now what's going to happen. So we've got that sort of idea. Excellent. Left-hand rule number 2, absolutely. So the north and south still works out for us. Now here's what happens in the armature. The armature is made out of a soft ferromagnetic material. And again, just like we saw before, all of the domains are going to align themselves with the magnetic field coming from the lifting electromagnet, and it's going to be attracted. So there's going to be a magnetic force, let me get a different color here, a magnetic force, FM, that is going to pull that armature towards our electromagnets. Perfect. Okay, so yep, that's kind of the same thing over and over again. So if that armature is feeling that electric force, so electric force FM is going that way, it's going to pull the whole thing over. It's going to have an electric force in the whole piece. The dinger, that's what I'm going to call that piece over there, also gets pulled closer. So look what happens now. It got pulled closer. The force pulled it this way, but is that force there anymore if we don't have any contact? Right? And that's why they call it a contact screw. Sometimes it's in contact, sometimes it's not. So can electrons get through there? Electrons cannot jump across when there's that empty space, and it's like closing a switch, or sorry, opening a switch. So electrons cannot get across. That means no current is flowing through the solenoids, and if no current is flowing through the solenoids, well, there's no magnetic force. So there's nothing to pull that over anymore, but we've still got this spring. So the spring, oh, that's the wrong direction, sorry. So the spring is going to have its spring force that's going to pull the dinger back. So it's going to pull, and this whole piece is going to move in this direction. So we've got the spring force pulling it back, and then it's going to come in contact again. So contact with the contact screw. As soon as it comes into contact with the contact screw, those solenoids have current running through them again, and we have a magnetic force, and guess what's going to happen? It's going to pull the dinger over, it's going to hit the bell, and it's going to go ding. So let's go back, let's clean this up just a little tiny bit. That's not cleaning it up. Clean it up just a little tiny bit, and I'll show you kind of how this works. So let's see, that way, and then that way. So we start off with this. We've got our magnetic force. It's going to pull the armature and the dinger over. Once it pulls the armature and the dinger over, oh no, I touched too much all at once. Okay. Sorry, folks, I was trying to be quick with that, and it didn't really work. Okay, so starting here, the magnetic force pulls the armature and the dinger over, and once it gets pulled over, well, there's no more contact in the contact screw. All that's left is the spring force, so that pulls it back, and then it hits the contact screw, and all of a sudden we've got current, and it goes back and forth and back and forth and back and forth between those two things, making the bell ring over and over and over and over again very, 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 very quickly. So there's electric bells for us. Cool, electric bell application. Next application, I believe this is the final application for this lesson, is our electric motors. So these electric motors, there's a whole bunch of them that you see in this picture over here. The common element that you see, even though they look a little different, is you see coil of wires, you see coils of wires in all of them. That one's literally just a coil of wires, coil of wires, coil of wires, coil of wires, whole bunch of coils of wires. So many different coils of wires inside of here, wrapped into there, coils of wires that you can see. It's all solenoids, right? Electric motors are just solenoids, realistically. So anything that moves and is electric has one of these. I'm telling you, it is like the most important invention, or one of the most important inventions for our modern day. So here's how it works. We've got a current carrying wire in an external magnetic field. So first and foremost, what hand rule does that make you think of? Current carrying wire in an external magnetic field. So for me, I automatically go to left hand rule number 3. And if we wanted to do a quick review, we've got our fingers, barely gonna have enough space for this, are the external magnetic field. We have our thumb is the current running through a section of the wire, and then I have my palm as the magnetic force. Cool. So, did I not put, determine the nature of the magnetic force in each part of the loop. Did I not put pictures of my hand on this one? Oh, okay, there we go. Just skipped it forward a little bit here. So essentially, let's go through and let's trace this out again. So I've got negatives going here, and the negatives are going up and into the page. They're going back into the page along that red line. Cool. And then I trace them around, and these are going to be the same electrons that I'm tracing around, but they come over through here, and then they're moving now in this direction, so that's out of the page on the left-hand side of the thing. So into the page and out of the page. Kind of hard to visualize with, again, 3D and 2-dimension stuff. It's kind of tough. But note that the red is going into the page, into, and the blue is coming out of. Okay, cool. So you got that figured out. So I know on the red section of wire and the blue section of wire, actually let's be very specific here, red section, and we'll get rid of those side pieces because they're parallel to the magnetic field, so they're not actually going to feel a magnetic force. We'll just check out the red and the blue. Cool. So get out hand rule number 3. We have two things. One of them is not really shown. So we've got the current. The current has to be going for the red wire, and let's focus on the red wire for the time being. Current for the red wire has to be going into the page. Which direction is the magnetic field? Maybe I'll use green for the magnetic field. So magnetic field is always from north to south, so magnetic field is going in that direction. So I get out my hand rule. Let's see, I've got hand rule, I got pictures of the hand rule over here. I need my current to be going into the page for that wire. So with this, my thumb has to be pointing in the page. No matter how I have this, how I rotate this, my thumb is always pointing into the page. That's the way it has to be, and I cannot move that. The next thing I need is my fingers to be pointing in the direction of the magnetic field. So the only way that I can have my thumb pointing into the page and my fingers pointing in the direction of the magnetic field is if I orient my hand like this. So take a second, make sure you're orienting your hand like this. And once we've got that, what's the only direction that our palm can face? If you're saying the only direction that the palm can face is upwards, you're absolutely 100% correct. So let's get this stuff out of the way. Cool, which means that the magnetic force on this side of the wire has to be upwards. Cool. Let's check out the blue side of things now. Let's try and figure out the magnetic force on the blue side of things. So I've got my other picture of my hand over here. Now the thumb needs to be, let's try making this a little bit bigger. Thumb needs to be, that's my current, pointed out of the page, and that's essentially what I've got here. No matter how I rotate this, my thumb is pointing out of the page. Now my magnetic field has to be going towards the right. So my fingers need to be pointed towards the right. So this is the orientation that I want for that. Thumb pointing out of the page, fingers pointing towards the right. What's the only direction that our palm can face once we set up our hands like this? And again, please try this out on your own. The only direction that our palm can face is downwards, which means on this side of the wire, we've got a magnetic force that is going downwards. Cool. You're probably already thinking to yourself, well, what's going to happen if one side of this loop of wires is pointing downwards, or the magnetic force on one side is downwards, on the other side is upwards? Well, hold on, let's go back there. Same as anything. So I've got this loop of wires. Hold on, I'm messing everything up here. I've got this loop of wires, and essentially on one side, we've got a magnetic force that's going upwards, and on the other side, we've got a magnetic force that's going downwards. You're going to see this thing spin on an axis around in a circle, right? And that's where we get the motion from these electric motors. Cool. Very, very good. Now, some of you are probably going ahead and thinking to yourself, well, if the current's always going the same direction through the same wire, we're just going to run into an issue and it's just going to stop, right? So what we have to alleviate this is something called a split ring commutator, or C-ring, so a split ring commutator. And what the split ring commutator does is it ensures that the current is always going the same direction on the same side of the magnetic field, right? So it's not going the same direction through the exact same piece of wire. It's going the same direction on the same side of the magnetic field. So if I'm closer to the south side, I may always be going this way, and if the wire is closer, whenever the wire is closer to the north side, I may be going that way. Let's check that out. This example might not show it very well as we go through and as we see. So step one, we've again got our, let's see, magnetic field, FM, going from north to south. Let's see, this is the negative side in this case. So I've got electrons that are flowing in this direction, and I'm really going to focus just on the part where they're in the magnetic field. So electrons going in that direction. So let's see, if we put our hands, take a second and see if you can make your hand work for this one. So electrons kind of going into the page-ish, magnetic field kind of going to down-ish and to the right. Not the greatest drawing. But the magnetic force on this particular section would be up, and the magnetic force on the other section, where the electrons are coming out of the page, is going downwards. So FM downwards. On the other side, oh, I made a screw up. That's not my magnetic force. What is that? It's my magnetic field. Common mistake that we've made there. Cool, so magnetic field, that's my fingers, going from north to south. Electrons, that's my thumb. Better label this side too. Electrons, that's my thumb. You can trace the path along there. Perfect. And we've got the magnetic force. Notice next to the north pole, the magnetic force is up, and next to the south pole is down. The next piece that we look at here is we don't actually see much in the way of a magnetic force at this particular point. So inertia carries it through to the next part where we actually see the magnetic force again. But notice what's happened here. The part that had, and this little section right here, that little extra piece, that's just to show which side it is. So the electrons before on this side, so I'm even going to highlight it here. let's use a different color. Let's use green. I don't see much green on there. So that little chunk right there, the electrons were going the opposite direction, right? But it was also on the opposite side. So you'll notice with this, with the split ring commutator, electrons are always, so next to the north, they're always going, where's the red, in this direction, which means the magnetic force is always going to be upwards on this side. Same thing with next to the south, the electrons are always flowing in this direction, which means that there's always going to be a magnetic force that's going downwards on that side. So it's going to keep spinning over and over and over and over again. So again, from here to the other side, electrons always flowing, and here's both of them at the same side, always flowing the same direction, closest to the North Pole and closest to the South Pole. So we always have an up magnetic force here, a down magnetic force here for this particular setup, and same thing on this side. So it will continue rotating around. So if this is the side view of my loop of wires, it will continue rotating around in that direction over and over and over and over again. Cool. So I hope this is not too confusing. I know that it is a little bit here. So just kind of put these up and you can read them if you need to. Yeah, it's not too bad. And you can check out other YouTube videos of this if you're having a bit of a hard time. But electric motors, we see them everywhere. We honestly see them everywhere. Anything that's electric and got moving parts. Very cool. Very, very cool. Okay, so keep them moving, keep them moving. This is all the same sort of pictures and same sort of ideas. And you've got that in your workbook. So anyways, that is the scoop. There's no practice for this one, which is kind of nice. But do make sure that you can explain how things work and use your hand rules to try and explain them. You'll see in the practice test, there's a couple little pieces for this. Anyways, that is it for now. We'll talk to you later, Physics 30s. Have a good rest of your day.